Hello everyone. I am Nilesh Kumar Sen, working as an assistant professor in ABES Engineering College, Ghaziabad. Our today's topic is translation Lookaside buffer. Sometimes it is also called as hardware cache. Means a cache memory which is implemented on the hardware. So till now, as we discussed about the phasing and segmentations, their drawbacks, advantages, virtual memory. As you can see that what we are doing is we are increasing the access number of access, we are increasing the head ratio, and we are decreasing what the time which is required to fetch the pages inside the main memory, as there are number of various such as less memory sizes available and number of pages are more. So on the basis of all such information, now we created something new or a different tool, which is what the translation Lookaside buffer, sometimes also referred as hardware cache. So as we know that a particular program or a process is converted into a number of pages. Those pages uh, are what is stored inside the page table, and those page table will maintain some entries. These entries or information about such as frame number, address of the main memory where we want to refer, and some useful bits such as valid or invalid bit. Valid or invalid bit, which is also known as present or absent bit, means a particular frame is available or not. Protection bit, that means whether the user is allowed to make any changes or not, means up to what extent the user is allowed. And reference bits are also there, caching enabled or disabled bit, and dirty bit, means whether the frame is modified or not. So there are 0 and 1 associated with all those information or the bit changes according to the frame number. So this page table entry will tell where in the main memory the actual page is residing. Where to place that page table is again remaining a question, such that the overall access time will be less. And our earlier problem was what? To fast access the main memory content based on the address generated by the CPU and its conversion from logical to physical one. So it is still remaining. So what we did now, we put, as you can see that CPU generates about the logical addresses, means page addresses and offsets one. So that page is checked inside the TLB. Whether the page is available or not. If that page is available inside the cache, then that page number will be referenced with some frame number, and that frame number will be called as TLB head and will generate a frame, particular frame at what we are looking for. And along with the offset, which we are again fetching from here, so will map to the physical address that at this very particular location our frame is residing. What if that page is not found in the cache? Then it will go to the page table, a page map table, which is again maintained as per the pacing till now. And from that pacing, it will be fed to the required one. And this is what the TLB miss. If page is found inside the cache, it is considered as TLB hit. And if that is not found inside the cache, so it is considered as TLB miss. So what is the advantage of doing so? Uh, Let us consider an example of MS Word and consider that each and every individual task is a page itself. Means uh, converting a text into the bold one is itself a page, italic, underline, and fonts, coloring, backgrounds, hiding, and so many tasks that we performed uh, using MS Word. So each individual task is considered as what the page. All those pages are not uh, cannot be stored inside the RAM. To do so, what we did till now, that most of the pages which are frequently accessed or frequently used are stored inside the cache. On the basis of cache, what we stored is the frame number, means actual code will be reside over here. And those which cannot be stored inside the cache will be kept inside the what the page table or page map table. So when as and when required, the remaining portions such as consider that word art. Let's suppose that word art is not kept inside the cache and word art is kept inside what the page table. So as we required word art now, so it will be called accordingly, and we'll make some space empty from here, and that word art will be filled. So this is how we are going to access cache, and by using TLB, it will enhance the access. So there are various steps involved in TLB hit and TLB miss. So one by one, we'll look into the TLB hit and miss also. So in TLB hit, CPU generates a logical address or a virtual address. It is checked inside the TLB whether it is present or not. As we are mm, learning about TLB hit, so it is considered that it will be present inside the TLB. The corresponding frame number is retrieved, which now tells where the main memory base lies. And what if that the page is not present? So it is considered as the agreement that we earlier discussed. So first step is what CPU generates a virtual address. It will always be the same one, and it is checked in TLB as it is TLB mesh, so it will not be present over there. Now the page number is matched with the page table residing inside the main memory. That is what the RAM is. Assuming that the page table contains all page table entries, so the corresponding frame number is retrieved. This now tells where the main memory page lies is. And the TLB is updated with the new page table entries. If a space is not there, so one of the replacement techniques come into the picture, that is either FIFO, LRU, MFU, optimal page replacement. There are various algorithms that we'll discuss later, but these are the techniques which we use to make a space empty. Now, the important thing, and from the university point of view, and most of the competitive exams point of view, that TLV is very important topic, and this formula is also very important to calculating for what effective memory access times. That how much time it requires to fetch the data. So TLV is used to reduce what the adequate memory access time. as it is a high-speed associative cache memory. As I've already discussed that it is what the cache, hardware cache is. So, uh, we are considering what um, actually it is taking the exact time, what time is required by the registers. So, but as registers can have uh, a limited size, cache is a bit larger than the register. So, effective memory at access time equals to what? H whole multiplied with C plus M whole plus 1 minus H multiplied by C plus NM. Now, one by one we discuss what are those terms are. So H is what the hit ratio of the TLB, M is what the memory access time, C is what the TLB access time, and N is what the present system label, at what label we are accessing. Means, let's suppose system label 1 is used for no page table, and 2 will be used for one page table, and 3 will be used for two page table. So you can say that for n minus 1 page table would be required. There's a numerical asked in a previous gate examination. We'll discuss now. Consider a paging system that uses one label page table residing in main memory. So here it is what the one label page. One label page table residing in main memory and a TLB for address translation. So what we are using is one label page table and TLB for address translation. Each memory access takes 100 nanoseconds and TLB lookup takes 20 nanoseconds. Each phase transfer, whether it is to or from the disk, disk to main memory or main memory to disk, is 5000 nanoseconds. Assume that the TLB hit ratio is 95%, means out of 100, 95 times the data is present inside the cache, TLB cache. And page fault rate is 10%. That means what the page is already there. So page fault rate is 10%. Assume that for 20% of the total page faults, a dirty page has to be written back to disk before the required page is read from the disk. TLB update time is negligible. Means fetching the information from the TLB is considering as negligible. Average memory access time in nanosecond, right, round off to one decimal place would be what? So given data is what the main memory access time, that was 100 nanosecond. TLB lookup time, that was what, the 20 nanoseconds. Time to transfer from one page to disk or disk to a main memory is 5000. TLB hit ratio converted 0.95. Page fault rate 0.10. 20% of page faults need to be written back to the disk. So effective memory access time, as per the formula, we will put the values and it will be calculated as what, 155.0. Another example. So as you can see in the question, that virtual address are of 64 bits long, physical addresses are 48 bit long, memory is word addressable, page size is 8 KB, and word size is 4 bytes. translation Lookaside buffer in address translation path has 128 valid entries. At most, how many distinct virtual addresses can be translated without any TLB mess? So TLB entry is what? Page number divided by frame number. Page number of frame number. So memory is word addressable, means word size is what given? 4 bytes. So and page size is what? 8 kilobytes. So 8 kilobyte will be converted into the word size, so it would be 211 words. Virtual memory size is what? 264 words. So number of pages possible would be 253, and number of bits required for the page number is 53 bits. Number of bits required for page offset would be what? 64 minus 53 would be will give you 11 bits. So at the time TLB contains what? 128. That means 27 distinct page numbers. If a page number is found in TLB, then there will be a head for all the words or word addresses for that very page. So the page head implies how many? 211 distinct virtual addresses head. So 27 page head implies how many? Since one page is required for 211, so the 27 page would require what? 27 multiplied by 211. So we'll give you these many virtual addresses. So maximum of these 256 by 210 distinct virtual address can be translated without any TLB mess. These are the references which I used to prepare the stuff